Hello, welcome to today's video on conic sections where we're taking it up a level because we're looking at those harder, longer, more problem-solving based questions that generally appear towards the end of an exam paper on this topic. Some things to bear in mind. I realised that there was several bits of advice I wanted to give on these sort of things, and I thought it would be too much to fit into one video, so I've split it into two separate ones. This is part 1 of 2, and the way I've decided to split it up is based on the fact that I'm aware that some colleges will split this chapter between the 2 years that they are studying it over. So this first video is more in line with what some colleges might be teaching in the first year, and then the second video might be more useful for just second year students. But if you are somebody who's learning all this stuff all in one big go, then you can watch both videos back to back by all means. Another thing to bear in mind that we have mentioned before is the fact that the conic sections chapter in general is almost just like an add-on to what you've already learnt before in Maths A-Level in the coordinate geometry chapter, where ultimately we're just occasionally doing that stuff with more algebra or with occasional cameo appearances from those new formulas to do with things like the focus and the directrix and stuff like that. But with that does mean that there's quite a wide range of things they can ask, so by all means I am not trying to claim that in this video I'm going to be able to show you every little thing they can ask. I'm just trying to give you some pointers to bear in mind when you are trying to approach a very sort of open-ended problem-solving based question in this particular chapter. But despite saying all that, admittedly after having gone through a large number of these questions over the years, there are a few approaches that I've noticed being used on multiple occasions that I've decided to pick out for you here today in case they are of any use. The first of which is one that should be very familiar with you: simultaneous equations. Of course, we're often used to just being able to rearrange one of the equations to make one the letters the subject of the formula, plugging that expression into the other one to eliminate that letter, and then boom, you've just got one equation with one variable that you can just go ahead and solve. However, in some occasions, for conic sections questions, you just need to be aware that sometimes you won't be able to substitute and eliminate all the letters in one big go always. Sometimes you might be able to do the substitution initially, but then optionally choose to not get rid of the remaining ones, just because the only way you'd have of getting rid of the remaining ones is to involve some really horrible powers and unnecessary things like that. So you get rid of the ones you can easily initially, leave the other ones behind, do a bit more rearrangement first, and then come back to substitute the remaining ones out later when it's more convenient to do so in a nice, easy fashion. So a quick example of that will admittedly be a bit of a silly one, because this is one you could do without doing the technique I'm about to show you, but I'm just doing it for demonstration purposes, just so you can see what I mean when I'm talking about having to do more than one substitution. Of course, you know, the easiest way of solving these simultaneous equations would just be to rearrange this one to be y equals or x equals, plug into the other one, and then, you know, there you go, easy. However, just so I can demonstrate about the idea of multiple substitutions, I'm talking about the fact that we notice in this first equation we've got 3xy, and then because the other one is just xy equals 2, then therefore instantly with barely any thought you should be able to look at that and realise that therefore that left-hand equation would just be x plus y plus 3 lots of 2, which is 6, equals 10, which then simplifies to, of course, x plus y equals 4. Now, therefore, as a result, we have got rid of some of the horrible stuff there, the most horrible stuff of all, because it was very convenient to get rid of. We still got a y left over in this equation. But that's not a problem, because now that's when we can choose to do the second substitution. Because we would now, after more rearrangement, choose to rearrange this one to make it y equals 4 minus x, which is then really nice because it can then be plugged into the xy equals 2 equation to mean we're going to end up with just x lots of 4 minus x equals 2, which is then really, you know, a very simple quadratic to solve. And as I said, we didn't need to approach this particular example in that particular way, but it's just me trying to demonstrate the idea of the fact you have to maybe sometimes choose to do a substitution, leave the other bit behind for the moment, do a bit more rearrangement to then come back to that substitution again at a later stage when it's going to be easier to do it. So there you go. The second bit of advice I want to give you, though, is that sometimes, although it seems a bit obvious to say this, if you're given information in the question, then it's something you're allowed to use to help to solve the question. The reason I say that is because a lot of people, when they are given information, will sometimes try to use it to set up an equation later in the problem, because they'll try to derive their own expression for that same bit of information and then compare it to the information given in the question to set up an equation. However, sometimes you don't want to do that. Sometimes it's more in your interest to immediately just sub into the given fact, because that will lead to an equation a lot quicker than having to do a load of steps beforehand to then set up maybe even a more complicated looking equation if you do it that way. So therefore, bear that in mind, and you'll see what I mean in the following example. So what I've got here is an exam style question that I've made, and just like a lot of exam questions, it's split into multiple parts, and also it is a long question. You can see already just by how much is written, there's several bits of information, which is to do with the fact there's also going to be several stages to solving this stuff. The part B, for instance, would definitely be worth at least probably 6 or 7 marks, maybe even 8, I don't know, but the point is it's a long question. You're not meant to just look at it and instantly know what the answer is, or even necessarily the entire approach to the entire question from doing it. It's just about being able to break it down, and that's part of the skill with stuff that I'm trying to demonstrate here. But the thing I'd like to point out is part A, they're asking us to find the equation of the normal to our curve C, which is a parabola, and we're trying to find the equation of the normal at a particular point. And the cool thing is, this is actually literally a question we already did in one of my previous videos. So, therefore, I'm actually going to be a bit cheaty, and I'm not actually going to go through the part A because I've already made a video on it. So, do just take a look back at that video. A link to it is appearing on the screen right now. But assuming that you are comfortable with doing part A, I'm just going to therefore quote what the answer to that is and focus on the part B. And also because the writing is taking a lot of room on the screen right now, let's all shrink that down so it's a bit more room for us to work with. So, the first bit of information they've given us in the question is the area enclosed between the curve C, it's normal at the point P, and the x-axis is 33/4, which is great news ultimately, because it means we already have a bit of information that you could start working with. You could start finding the area yourself and start setting up some equations, all that sort of stuff. But the downside to reading all the information at the beginning is admittedly that you can get a bit of information overload and it can get a bit confusing. So something that can help with that is drawing a diagram to help break down the information you have already read, and so it doesn't blur into one with all the other stuff you're going to read later. So we've got the curve C, it's a parabola. Of course, it's those types of parabolas that we've been dealing with before in conic sections that are basically quadratics turned on their side, because of that y squared equals rather than y equals. And then we got a point P. Now, I don't know where point P is, doesn't really matter, because ultimately it's effectively any point on the curve, because you might notice that those are effectively the parametric equations of the curve, so it's any point in the curve really. And we're finding the normal to the curve at that point, so therefore that'll be a straight line 90 degrees to our curve. So we are told that the area between the curve, the normal, and the x-axis is a particular number. So they are, for instance, talking about this particular area here. I've only shaded one side of the x-axis rather than both sides of it, because ultimately if they meant both sides shaded at the same time, they would have said just the area enclosed between the curve and the normal. They wouldn't have mentioned the x-axis as well. So because the x-axis is mentioned, it's forming part of the boundary for the area we're talking about. Cool. It also mentions the rectangular hyperbola R has equation xy equals 9. So we've got a second curve that's going on about. We're given that the curve C, the parabola we already had at the beginning, intersects with this new curve R at the point P. Find the coordinates of P. Okay, now that's interesting because it actually means, by luck, where I drew my point is roughly in the rough correct area of our diagram. Because we know it's a rectangular hyperbola of the form xy equals 9, we're talking about a curve that looks, oh goodness me, that's terrible axes. We're talking about a curve that looks something like this. And ultimately, the only way a rectangular hyperbola like this can intersect with a parabola of the form y squared equals 4ax, if a is a positive number, is if they do intersect in the top right-hand quadrant. So actually, therefore, that means by complete luck, where I drew P is in the correct quadrant, basically, for where I needed it to be. The interesting thing about this, though, is it does throw up another dilemma, because we would want to find what that point of intersection is, because that's going to be important, because that is the point P, according to the wording of the question. But therefore, some people might be tempted to just launch into doing simultaneous equations between the equation of the hyperbola and the equation of the parabola we're given, and solving that to get an expression for p, and then setting up an equation, etc., etc. But you don't need to. See, the reality is we already have some information about point P, the general structure of the coordinates of what P could be, and then we already know it lies on the rectangular hyperbola we're given below. So therefore, as it's a point of intersection, it must be part of the curve, and therefore it must be able to satisfy the equation of the curve. So therefore, we already know that those coordinates must be able to be plugged into the equation and work in the equation. So therefore, that's what I mean about using the given information and substituting stuff into it rather than always just trying to derive things for yourself and then compare with the information later. So therefore, actually, the very first thing I'm going to do is something very, very easy. I'm just going to plug those coordinates directly into x, y equals 9. So therefore, at squared x times by y, which is 2at, has got to equal 9. So therefore, we know 2a squared t cubed equals 9. So we've already got an equation without having to do loads of solving beforehand. So there we go. That's putting the bit of advice I said earlier into action already. Right, okay, so we've made use of that second bit of information now and done as much as we can with it. We've already managed to get one equation that suspiciously has 2 letters, almost as if we're going to have to do simultaneous equations later, but we'll deal with that when we get to it. We'll now go back and deal with that first bit of information again, because we hadn't dealt with that really at all yet. We realised it was the bit that I had shaded inside this curve, and we need to find that area. But we hadn't done anything more with it. Now this time, there's nothing really we can do in terms of directly substituting something into that bit of information. For the second bit of information, we had a curve to substitute into, but this, we're told what the area is, but we've got nothing to compare that to at all. So this is a case where we are going to have to find for ourselves what the area is and then compare it to that 33/4 later. So we're going to need to find that area, and the best way of going about that would be to split it into 2 chunks, because there's that first bit here, which is the area under the curve, or between the curve and the x-axis I should say, and then there's this separate bit here which is just the area of the triangle. So therefore that's going to be our next focus, finding that area but doing it in 2 parts. So, creating more room for ourselves again, to find that area, or to find the area between the curve and the x-axis, we're going to do integration. So again, making use of skills from Maths A level that we've come across before. Of course, though, if you want to find the area between the curve and the x-axis, you normally have to integrate the equation y equals with respect to x. You're not actually integrating the y, you're representing what y is equal to, and integrating that across the interval for which the area is lying. Of course, our equation isn't y equals, so the first thing you might want to do is rearrange to make it y equals. To do that, we could square root both sides, which looks very scary until you remember the index law, which allows you to square root the individual things. So therefore, that means we have 2 root a lots of x to the power of a half is our equation. So that's the equation of the curve we are integrating, but the interval we're integrating over is that we're starting, as you can clearly see, because it's starting at the y-axis, that's starting at x equals 0, and because we're stopping here in this region, that's obviously at the point P, where the point of intersection happened. So we're going to be integrating from 0 to the x-coordinate P, which is at squared. And therefore integrating to root a x to the power of a half dx. So we can now just go ahead and do that. So add 1 to the power, divide by the new power. So half plus 1 is 3/2. Dividing by 3/2 is same as timesing by 2/3. So therefore we get 4/3 root a out the front now. And then we've got our limits to plug in, making sure our notation's correct by doing the square brackets, and then plugging that stuff in. We get 4/3 root a, lots of at squared to the power of 3/2. And then we're going to take away what happens when you plug 0 in. Luckily, if you plug 0 into that, you just get 0. And so we can go ahead and continue simplifying it. So therefore, we can apply index laws to the stuff that's inside those brackets. So we can do a to the power of 3/2, which is just a root a. And we can apply t squared to the power of 3/2 separately as well, which will just get you a t cubed. And that's nice because we have a root a times by an a root a, which will just get you an a squared. So we have 4/3 a squared t cubed. But we should be aware that that isn't the full area. We also need to work out the area of the triangle that we have there. Now the triangle is quite nice to work out because it's going to be a triangle with a height of just the y coordinate p, because the bottom of the triangle is at y equals 0 and the top of the triangle is at p. Therefore that height difference is just decided by the y coordinate of p. And then the base, well, we know the base starts at at squared, but then finishes at the y-intercept of the normal. So we're going to need to find the y-intercept of the normal. And at that point, it's quite useful that we had already found the equation of the normal 2c at the point P in part A. Obviously, we didn't do that this video, it was in the previous video, but anyhow, the answer is there on the screen, so we're going to use it. So finding the x-intercept is when y is equal to 0. So we get this, and therefore to get x, the x-coordinate of the x-intercept, we just have to divide both sides by t. So therefore x is equal to 2a plus at squared. So therefore, if our triangle has got the point P at the top, which has got the coordinates at squared, 2at, and its base is therefore starting at at squared, and therefore finishing, we now know, at this x-intercept, which is at 2a plus at squared. Therefore, we now have all the information we need to work out the area of the triangle, because it's just going to be half base times by height. So therefore, area of the triangle equals the half times by its base. Now, its base is going to be 2a plus at squared minus at squared, because that will then just work out the length in between these 2 points. And then multiplied by the height, and the height, well, it's starting at y equals 0 and finishing at 2at, according to the y coordinate of p. So therefore, that's just a height of 2at. So therefore, we can work out that, and we can multiply stuff out. So therefore, it's going to be the half times the 2at is just an at, and then we have 2a plus at squared minus at squared is just 2a. So therefore, the area of the triangle is just 2a squared t. So therefore, we can now work out the total area between the curve, the normal, and the x-axis, because it's going to be the area we found as part of integration, which was 4/3 a squared t cubed plus 2a squared t from the area of this triangle added on. So that's what we got the area to be, but the question told us that the area is equal to 33/4. So therefore we can set up an equation, and so therefore that's interesting because it now means we've got this bit of information involving a and t, which we know must be true. We have the other bit of information from earlier in the question, which said that 2a squared t cubed must equal 9, and so therefore these two things combined now mean we have enough information to be able to start trying to solve this question, because it's just going to be simultaneous equations between these two things. And this seems like a convenient time to refer back to the advice I gave earlier in the video about sometimes wanting to do multiple substitutions to solve simultaneous equations. It's worth making the disclaimer that I'm by no means saying that you can't solve these equations by doing the traditional approach of rearranging one of them to be one of the letters as a subject to the formula and plugging it into the other one. But what I'm saying is it's funny because students are always telling me, oh, I can't be bothered to write this line of working because, you know, that's too much effort or whatever. And you see, there's often times in maths where instead of just rushing in, you can be a bit more tactical, take a step back, and then realize there's certain things you can do which will speed things up and actually require you to write less stuff. So yes, you could rearrange to make t equals the subject of the formula for one of these equations, but then that will lead to more horrible powers, or even a equals. That would be a lot nicer, but even then, there's something even nicer we can do to simplify things more quickly by realizing that there are a couple of letters in a certain pattern together that is appearing in both equations that we can just immediately replace, therefore meaning we have to write less. So do watch out for that. From this first equation, we get a squared t cubed equals 9 over 2, which is something I can just substitute into just this bit, because that's a nice easy substitution to make without doing anything too crazy. So therefore, if I was to do that now, we'd end up with 4/3 lots of 9 over 2 plus 2a squared t equals 33 over 4. 4/3 lots of 9 over 2 is just 6. And then from that, we end up with 2a squared t equaling 33 over 4 minus 6, which is just going to be 9 over 4. And therefore a squared t is equal to 9 over 8. Nice. So now we've got this equation. This is much nicer than what we had before. Still 2 letters, but then easier to deal with when in conjunction with the other simultaneous equation we developed earlier. And therefore it's now going to be a lot easier to deal with, because as you might notice, there's going to be a very easy way we could eliminate the a squared. So we could rearrange to ultimately do the substitution I could have done much earlier, but now it's going to be even easier to do if I'm choosing to do it at this stage instead, because I could rearrange this second equation to make it a squared equals, that's just going to be 9 over 8 lots of t, which means when I plug that into the other equation, we're going to end up with just 9 over 8t lots of t cubed equals 9 over 2. That means I could now simplify that to get 9 over 8 t squared equals 9 over 2, which gets even better because it means I'm just going to have t squared equals 4, which means t equals plus or minus 2, and then we can find the values of a squared by plugging into a squared equals 9 over 8t. So therefore, first of all, doing that with t equals 2 will get us a squared equals 9 over 16. Or, of course, we could plug in t equals minus 2, but if you do that, that's implying that our a squared value is negative, which of course is not possible. So therefore, we're going to reject this possible value for a squared, and therefore actually we're going to reject t equals minus 2 in general, t equals 2 only as a result. So therefore we get t equals 2 with either a is equal to the square root, plus or minus the square root, I should say, of 9/16, which is plus or minus 3/4. And it would be very easy for us to then say we're done, but read the question, be very careful, we're not done. Although we've found the value of a and t, that is not what we were asked to find. We were asked to find the coordinates of p, and although a and t are helpful for finding them, they themselves aren't the coordinates. We need to plug those values of a and t back into this structure that we had up above. So doing that, you will get the final answers of 3, 3, or minus 3, minus 3, plugging the values of a and t back into those coordinates. Okay, and therefore we are now finally done, and that is all I wanted to cover today. Hopefully the chance to see me doing some problem solving there was helpful. Not really actually that much problem solving, but just how to deal with a bigger question, being able to break it down, and little tips and tricks to just speed up the process and do things in a nice efficient way, hopefully maybe even helping you avoid silly mistakes along the way as well. So there you go, those are things to watch out for Conic sections, and I will see you in a future video. Goodbye.